Okay, let's do this turbine problem. With this turbine problem, this is an example that I really like to show, but because it kind of explains to us why we neglect certain terms in the first law for open systems. What we have here is we have a turbine with realistic values at the inlet and the exit. We're going to calculate the magnitudes of delta H, delta KE, and delta PE, and we're going to compare and see how those magnitudes compare to each other. In this example, we'll be able to see clearly why we typically ignore kinetic energy and potential energy for devices like a turbine and a compressor and several other of the devices that we've talked about in Chapter 4. Okay, let me start off. We'll read this problem statement. It says we have the power output of an adiabatic steam turbine is 5 megawatts under the operating conditions shown below. We want to compare the magnitudes of delta H, delta KE, and delta PE. What does this tell us about the system and other systems? Also, we want to determine the work per unit mass and the mass flow rate of the water passing through the turbine. So these are the properties that were given for the turbine. We're given some properties at the inlet, some at the exit. At the inlet, we're given pressure, temperature, velocity, and elevation. At the exit, we're given pressure, quality, velocity, and elevation. So let's go ahead and we'll set the problem up first thing. Our system here is, this says we have an adiabatic steam turbine. So steam turbine just means that at the inlet we have superheated water vapor. So our system here is actually water. Our device is a turbine. Water is a phase change substance, and the turbine is an open system. For the sketch, that would be what was next. On our sketch, basically this is exactly the sketch that we would want to provide. It's an engineering sketch. It shows what we have at the inlet, what we have at the exit. If we want, we can go ahead and just make it super clear that this is the inlet number 1 and this is our exit number 2. So we'll say that the sketch is pretty much provided. For the conditions, what we want to do is we want to apply the chapter specific condition where we have a steady flow device. In this problem, I don't think it says anything about steady flow, but all of the problems that we're solving in Chapter 4, we assume steady flow even if it does not say so. So we have a steady flow device, and then we go to our notes and see what type of assumptions we make for a turbine. In general, for a turbine, we assume that the turbine operation is adiabatic, and in this case that is true definitely because the problem says it's an adiabatic steam turbine. So since it's adiabatic, that means that there is no heat transfer. Also, typically for a turbine, we neglect the kinetic energy and we neglect the potential energy change. But this is a unique problem where it actually wants us to calculate the kinetic energy change and the potential energy change. So that's the only condition that will apply specific to the turbine, is that we have an adiabatic process. For the properties, we are basically given all the properties that we need right here, right? We have all the properties at the inlet, all the properties at the exit already listed. The only other thing that we notice that we're given about the turbine is we're given that the power output is 5 megawatts. So we can kind of show that on the sketch. It says this is the power output, that is capital W dot, and then we can mark it down here that the power output is 5 megawatt. So 5 megawatt, we'll go ahead and put that into kilowatt. 5,000 kilowatt. That's our power output. And since power, right, follows the same convention as work, output work is positive. So we have power is 5,000 kilowatts. It's positive because it's an output work. And then all of our other properties are already listed. So we don't really need to repeat them. Now we're ready to solve the problem. And basically it first asks us to calculate delta H, delta KE, and delta PE. So those are things that we're going to be looking for. Also, we are trying to determine the work per unit mass. So that's a lowercase w. And we also want to know the mass flow rate. Alright, so these are 5 things that we're looking for. And now what we want to do is go through our general analysis like we do for all of the Chapter 4 open systems. So what we have, we start off with the mass balance equation. So for the mass balance equation, think about what type of device it is. A turbine is one inlet, one exit. So we write the single stream mass balance equation. M dot 1 is equal to M dot 2. Or in other words, we have a constant rate of mass flow through our device. So the mass flow rate is one thing that we're trying to solve for. We can try the mass flow rate equation at the inlet or the exit to get the mass flow rate. So we have V1 A1 divided by specific volume at the inlet or the exit. If we look at these properties, we do know velocity at the inlet, velocity at the exit. Also with the specific volume, that's probably something that we can look up based on the pressure and temperature at the inlet, or for the exit we could look it up based on pressure and quality. But what about the area of the inlet or the area of the exit? Do we have any information or any way to calculate either A1 or A2? Turns out that we don't, right? Area is an extensive property, so it does not depend on things like pressure and temperature or specific volume, anything like that. So there's no way that we can calculate the area unless we were given information about the diameter of the inlet or some other piece of information. So it turns out the mass balance equation with the mass flow rate equation is not very helpful. It doesn't actually allow us to solve for the mass flow rate in this problem. So we'll just have to keep going and see if there's another way that we can solve for the mass flow rate by some other means. Alright, next thing we want to write is the energy balance. And with the energy balance, we start off with the single stream, one inlet, one outlet equation. Q minus W is equal to delta H plus delta KE plus delta PE. And we apply our conditions for the turbine. We assumed that it was adiabatic. Normally for the turbine we would cancel out kinetic energy and potential energy change, but in this problem it's a little bit unique. It wants us to calculate these two values. So we'll leave them in the first law for now. Alright, let's go ahead and try to calculate these three terms individually based on properties that we know. We'll start off with delta PE. So just the equation for the change in specific potential energy looks like gravity times Z2 minus Z1. So we know the gravity, that's just 9.81 meters per second squared, and we're given elevation Z2 and Z1. So we can just plug this straight in. We have 9.81 meters per second squared times, here Z2 minus Z1. Z2 is given as 6 meters, Z1 is given as 10 meters, so we have a negative 4 meter difference between Z2 and Z1. So this turns out to be negative 4 times 9.81, and then we have meters squared per second squared. So we looked at how to convert meters squared per second squared to kilojoule per kilogram in the last problem whenever we were solving for the diffuser. Anytime we have meters squared per second squared, we need to convert that to kilojoule per kilogram. Right? All of the things like work per unit mass and delta H, those have units of kilojoule per kilogram, so we need to make sure that our units are correct. In order to convert meters squared per second squared to kilojoule per kilogram, we'll have to multiply by a conversion factor. So this is actually going to end up 9.81 times negative 4, and then our units were meters squared per second squared. We multiply that by our conversion to kilojoule per kilogram. 1,000 meters squared per second squared is 1 kilojoule per kilogram. If you don't remember how to do this conversion, I showed this conversion in the diffuser example, so you can go back and review that from the diffuser problem. Alright, so now that cancels out our units and we get back our answer in kilojoule per kilogram. So let's go ahead and take this to the calculator and we can try to figure out what is the change in potential energy. Alright, so the change in potential energy is just equal to 9.81 times negative 4 and divided by 1,000. So change in potential energy looks like negative 0.04. kilojoules per kilogram. That was one thing it wanted us to calculate, so we'll circle that. Next we can look at the change in kinetic energy. Change in kinetic energy looks like 1/2 times V2 squared minus V1 squared. So we are given both velocity at the inlet and the exit. We can just plug those values in. We have 1/2 velocity at the exit, number 2, was 180 meters per second. And we're going to square that. Then minus velocity at the inlet was 50 meters per second. Anytime we have velocity in the equation, we got to be careful with the units. Said this before with the diffuser example. So here we have velocity in the equation, and our units turn out to be again meters squared per second squared. So we also want to multiply this by our conversion and bring it down on the next line, that 1,000 meters squared per second squared is 1 kilojoule per kilogram. So that cancels out the units here, and we'll get back our answer in kilojoules per kilogram. So the change in kinetic energy is this is equal to 1/2 times 180 squared minus 50 squared. Then we divide that by 1,000 to convert the units. So the change in kinetic energy, a little bit bigger, we get about 15 kilojoules per kilogram. And it's positive. So already we see that the change in kinetic energy is much, much bigger than the change in potential energy. So already potential energy, we could say, is pretty much negligible. So let's compare these two numbers, change in potential and kinetic energy, to the third one that it wanted us to look at, which is delta H. So delta H is just H2 minus H1, and then the substance we have here is water. So for water, we calculate H1 and H2 based on the states and the properties. So if we look at our conditions for inlet number 1, our properties at inlet number 1, our properties at inlet number 1, intensive properties, are pressure and temperature. Also, we know that at the inlet we have steam because it says this is an adiabatic steam turbine. So we have pressure 1 is equal to 2 megapascal. Temperature 1 is equal to 400 degrees Celsius. And we know already that it's superheated. And pretty much every time that we look at a turbine, it's either going to be a superheated steam at the entrance, or if we're talking about a gas turbine, of course it's just going to be already superheated for a gas like air or nitrogen or oxygen or anything else like that. Alright, so based on the pressure and the temperature and superheated phase, we can go to the table, so look up H. H1 is just going to be enthalpy at P1 and T1. So to the tables, we need to scroll up to our pressure table, superheated. We want to look for 2 megapascal. So here's the 2 megapascal table for pressure in the superheated. Our temperature was 400, that's right here, and then specific enthalpy is the third column. So we get 3247.6. kilojoule per kilogram. For the outlet, the properties we know at the outlet, intensive, are pressure, and we also know the quality at the exit. Our pressure at the exit, P2, is just 15 kilopascal, and the quality at that exit is 0.9. So we already know the phase at the exit is a saturated mixture. And again, if we have a steam turbine, pretty much the way that you'll see it is you have steam at the entrance, superheated, and then at the outlet of a steam turbine you'll usually have a high quality saturated mixture like this, or in some instances you still may have a superheated vapor. Most of the time you'll get a high quality saturated mixture at the exit of a steam turbine. So to get the enthalpy, specific enthalpy at P2 and X2, we're going to have to use the quality equation. H2 is going to be something like HF2 plus X2 times Hg2 minus Hf2. Or if you want to use a little bit of a shortcut with enthalpy, we're also given the vaporization value. So we could write this as Hf2 plus X2 times Hfg2, where this Hfg is the same thing as Hg minus Hf, but Hfg is given its own column in the saturated water tables. So let's go to the saturated water table, see if we have pressure of 15 kilopascal. So 15 kilopascal, that's going to be 0.15 bar. So we don't actually have values at 0.15 bar. We have values at 0.1 and 0.2. So we'll have to do a little bit of interpolation to get HF2 and HFG2. So let's do HF2 first. For HF2, we're going to be interpolating. our table value is 0.1, our value is 0.15, other table value is 0.2, and then at 0.1 we have HF of 191.83. At 0.2 we have a table value of 251.40. So there's HF2, we're going to have to interpolate it. And then for HFG2, also going to need to interpolate 0.1, 0.15, and 0.2. So the table values, and then 0.15 is our known value. At 0.1, HFG is 2392.8. And at 0.2, HFG 2358.3. So let's go ahead and plug this stuff into our calculator to get H2. So first of all, let's do HF2. So for HF2, we're going to be interpolating 0.1, 0.15, 0.2. Then our values 191.83 and 251.4. So there's HF2, 221.6. And then for HFG2, we were interpolating 0.1, 0.15, 0.2, 2392.8 and 2358.3. So here's HFG2, it's 2375.6. 2375.6. So that leaves us with an H2 value equal to HF2 plus X2 was 0.9 times HFG2. So our H2 value turns out to be 2359.6. And that's in kilojoule per kilogram. So now we can calculate delta H. It's equal to H2 minus H1. So delta H is equal to H2, which we just calculated, minus H1. H1 was 3247.6. So delta H is negative 888. And that's in kilojoule per kilogram. Alright, so now we have three things. We've gotten delta H is negative almost 900. Delta KE, much smaller, it's at 15. And then delta PE, even smaller than that, it's 0.0 something. Alright, so now we can basically see why, for the most part, in the turbine problem and the compressor problem, also other problems, there may be a change in potential energy, there may be a change in kinetic energy, but those values are so small compared to the dominant term, like delta H, that it's essentially negligible. So let's kind of summarize this. We've seen that delta PE is much smaller than delta KE, which is much smaller than delta H. This is why we can ignore delta KE and delta PE in a lot of systems. So we can just say in many applications. So this just goes to show why those assumptions or those conditions that I tell you for different devices, why they are good assumptions. Alright, so that finishes up the first part of the problem. We've calculated delta H, delta KE, and delta PE. But we still have to solve for the work per unit mass and the mass flow rate. So the one that we should be able to solve pretty quickly would be the work per unit mass, because we have all of these three terms now. So calculate the work per unit mass is just going to be negative delta H plus delta KE plus delta PE. Just plug that into our calculator. Work is equal to negative delta H plus delta KE plus delta PE. So we get that the work is 873 kilojoules per kilogram. And it's positive, which is good, because that means it's an output work. And we know that the whole purpose of a turbine is to produce work. That's why we get an output work. If we had neglected kinetic energy and potential energy, we would have found that the work per unit mass was just equal to negative delta H, and we would have got negative times negative, so we would have got positive 888. So by neglecting kinetic energy and potential energy, our answer basically went from 873 to 888. So that's why we can neglect kinetic energy and potential energy in most applications, is because we're just trying to get a really good estimate, not trying to be super precise most of the time. Alright, but we're still left with the problem, how in the world do we solve for the mass flow rate? We tried applying the mass balance, didn't get anywhere. We tried applying the mass flow rate equation, and we still don't know the area of the inlet or the exit. So sit down and think about this for a second. How can we solve for the mass flow rate based on what we know? So is there any other information that we know about the system that we haven't made use of? We've made use of all of the properties. Here we go. We haven't made use of anything with the power. So is there a way that we can use information about the power to calculate the mass flow rate? Turns out that that's exactly what we need to use in order to calculate the mass flow rate. So if you remember, I gave you an extra equation for a single stream device. We know that there's a relationship between the work per unit mass and the power output. For a single stream, the work per unit mass times the mass flow rate is equal to the power. And in this case, we know both power and the work per unit mass, so we can solve for the mass flow rate this way. That means our mass flow rate is just the power, which was 5,000 kilowatt. We want to make sure that we're using kilowatt, not the megawatt number, because our work per unit mass is in kilojoule per kilogram. Divide that by the work per unit mass, and we get the mass flow rate is 5.73 kilograms per second. So if you want, you can check the units on the power. The power is in kilowatts, which is actually kilojoule per second, and then we divide by kilojoule per kilogram. So the kilojoules cancel out, kilogram comes back up to the top. That's where we get kilograms per second. So this wraps up the turbine problem. Again, we use the mass balance and we use the energy balance to study the system. We also showed why kinetic energy change and potential energy change are neglected in most of the systems that we look at. There's only a couple systems where the kinetic energy change is important, and that is the nozzle, the diffuser, and those are the only ones that show up on exam 2. The ones where kinetic energy is important is the nozzle and diffuser.